In this lesson, we're going to talk about the binomial distribution, and we're going to introduce it by considering one example. Consider the random variable x that is defined as the number of sixes obtained after tossing a die 5 times. We're going to consider getting a 6 a success, and we're going to consider not getting a 6 a failure. So in this case, in this kind of experiment, we only have two options. We're going to have a success if we get a 6, and we're going to have a failure if we don't get a 6. Now let's think about the probabilities for these two scenarios. We have success and failure. The probability of success is going to be the probability of getting a 6 when we toss a die 1 time. That probability is 1/6. Now the probability of a failure is going to be 5 out of 6. Remember, we can either succeed or fail. So these two probabilities need to complement each other. One thing that we can observe is that the probability of getting a 6 each time we toss a die is not going to change. It's not going to be affected by the previous result, and is not going to change by different circumstances. The dice is not changing, so the probability of 1/6 is not changing. One more thing that we need to acknowledge about this random variable is that the random variable is setting how many times we are tossing the die. This time it's a finite number and it's 5 times. Keeping the number of trials in mind, we can use this information to create the probability distribution for the random variable x. We know that the possible outcomes for the random variable x is 0 sixes, 1 6, 2 sixes, 3, 4, or 5 sixes. So we need to figure out what are the probabilities for each of those events. Let's try to focus right now on one of the outcomes. Let's say we want 3 sixes. We want 3 successes. If we want to find the probability for 3 successes out of the 5 attempts to the experiment, then we need to consider, for example, the scenario when we get success, 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 and then 2 fails. This probability is going to be calculated by the product of 1/6 times 1/6 times 1/6 for the successes, and times 5/6 times 5/6 for the 2 failures. This is, however, not the only combination in which we can have 3 successes. I have 5 trials, out of which I want 3 of those to be successes. This is calculated through the combination of 5 and 3. So in order to get the probability when x is equal to 3, we need to consider all of these combinations. So we're going to calculate the combination of 5 and 3, or 5 choose 3, times the probability of success, and this is going to go to the power of 3 because we want 3 successes, and times the probability of failure, 5/6, to the power of 2 because we want 2 failures. With this in mind, we can use the same logic for all the other outcomes in this probability distribution. So how can we generalize for either of these probabilities? How can we find the probability distribution function for this particular random variable? So we're going to calculate the probability of x equals x as the combination of the number of trials, how many successes do we want, let's call that R, times the probability of success, we're calling it P, to the power of the number of successes, R. And then times the probability of failure, 1 minus P, to the power of the number of failures. In this case, the number of failures would be n minus R. This probability is called a binomial probability. And variables like this random variable x are binomial variables. We are going to say then that x is binomially distributed with the number of trials n and probability of success p. Now that we have the general expression for the probabilities, we can move on to fill in the table. Now let's summarize all of our findings. A random variable x is binomially distributed if there are only two options for the experiment that we're performing, a success or a failure. The probability of success and the probability of failure are constants and have the same value for each of the trials. Additionally, there is a fixed number of trials. We know how many times we're performing the experiment. If these conditions are met and our variable is binomially distributed, then we can find the probability distribution function through the expression shown here. We need the combination of the number of trials and the number of successes times the probability of success to the number of successes that we desire times the probability of failure to the power of the number of failures that we desire. Now, to complement this information, we would like to know how can we calculate the expected value for a binomial distribution and how can we calculate the variance for a binomial distribution. If we construct the table like we did in the previous example, we can use the formula sum of x values times the probability values to calculate the expected value. Of course, that is still valid. However, we can also try to work things out to see if there is something special about this kind of distribution, some particular pattern that we can identify for the calculation of the expected value for a binomial distribution. So what we're going to do is we're going to start by considering this expression for the expected value that we have as a sum of all the outcomes times the corresponding probabilities. And we're going to substitute the probability with the quantity that we found before, shown here. So we are going to get that the expected value is going to be the sum of x times the combination of n and x. In this case, remember, x is the number of outcomes times the probability of success to the power of x times the probability of failure to the power of n minus x. Now we can write explicitly this combination. N factorial over n minus x factorial times x factorial. And what we can do now is try to simplify the x that we have here with the x that we have in this factorial. Then the expected value is the sum from x equals 1 to n of n factorial over n minus x factorial times x minus 1 factorial. Everything else remains the same. Now I want to define two new variables. I want to define the variable y as x minus 1 so that x is going to be y plus 1. And I also want to define the variable m as n minus 1 so that the variable n is going to be m plus 1. With that change of variables, our sum becomes the sum from y equals 0 to m of n factorial changes to n plus 1 factorial over n minus x factorial changes to m minus y, x minus 1 changes to y, and p power x changes to p power y plus 1, and 1 minus p changes to 1 minus p to the power of m minus y. Looking at this expression, we can take n plus 1 and p out of the sum, n plus 1 and p out of the sum, and we get m factorial over m minus y factorial times y factorial, p to the power of y times 1 minus p to the power of m minus y. If we look at this sum, this looks like the expansion of a binomial. So we can compare this sum to the sum a plus b to the power of m. This is going to be the sum from y equals 0 to m of the combinations c, m, y times the value a times b to the power of m minus y. So in this case, the role of a and the role of b is being taken by the values p and 1 minus p. So if we think of this as a binomial expansion, we can substitute this sum with this binomial. So the expected value of x would be m plus 1 times p times the binomial p plus 1 minus p to the power of m. Now we can see that this is going to simplify to m plus 1 times p because p minus p cancels. 1 to the power of m is 1. Then we can substitute the value of m with n minus 1, and we get n minus 1 plus 1 times p. Therefore, the expected value for a binomial distribution is going to be n times p. This is a very important result. The expected value of a variable that is binomially distributed can be found by the product of the number of trials times the probability of success. Now it's your turn. Given that x is binomially distributed with n number of trials and a probability of success equal to p, can you find an expression for the variance of x? Let me know what you find next time in class.